So in this video I will be discussing exercise 1.2. So I am starting with the first question. Express each number as a product of its prime factors. So exercise 1.1 question number 1, I am taking the second one. Okay, 156. We have to express this one as product of its prime factors. Okay, so this is nothing but prime factorization. 2 7s are 14, 2 8s are 16, 2 3s are 6, 2 9s are 18, 3 1s are 3, 3 3s are 9. So here we are left with all prime numbers. It means that it can be stopped here. Therefore 156 is equal to 2 into 3 into 13. Okay, so this is the prime factorization of 156. Done. Okay, now let us move on to the next question. So the second question is find the LCM and HCF, and then we have to verify that HCF into LCM is always going to be the product of two numbers. So let me take the second one. Okay, I am taking the second one. That one is 510 and 92. So what we need to verify? To verify HCF into LCM is equal to product of the numbers. Product of the numbers. Okay, so let us start with 510. Do the prime factorization. Similarly go for 92 also. Okay, 2 2s are 4, 2 5s are 10, 2 5s are 10, 5 5s are 25, 5 1s are 5. So 13. No, 13 is not going to give you anyone. 13 7s are 51, 17, 3 17, 3 3 17. Yeah, 17 3s are 51. Done. 2 4s are 8, 2 6s are 12. Just 6. Done. 23. So we have done the prime factorization of 510 and 92. So we can write 510 is equal to 2 into 5 into 17 into 3, and here 92 can be written as 2 into 2 into 23. Clear? Now we have to find out the HCF and LCM of these numbers. So what can we say? Highest common factor, HCF is how much? Only 2 is common. So our HCF is 2. Now what about LCM? LCM will be 2 into 5 into this entire thing, isn't it? 2 into 5 into 17 into 3, this entire, and we will be left with this 2. 2 into 23. So this is total LCM. Okay, have you understood how LCM, lowest common multiple, isn't it? So since 2 is common, so we will be taking these 2 once, and the remaining all these prime factors will be coming for LCM. All of you know these things very nicely. So we got the HCF, we got the LCM. Now we have to show that the product, if we find out the product of HCF and LCM, that will be equal to the product of the numbers. So we have to multiply the numbers, and then we have to multiply the HCF and LCM also. Now we shall start. Okay, now HCF into LCM is equal to how much? 2 into 2 into 5 into 17 into 3 into 2 into 23. Okay, this 2 taken, and here after that 2 5 17 3 to 23. Okay, let us find out the product. 2 2s are 4, 4 5s are 20, 17 to 34, 340, 3 2s are 6, 6 3s are 18, 12 and 13, 138 and 340. So do the multiplication and find out. 138 and 34, 8 4 32, 3 4 32, 15, 5 5 8 6 8 24, 2 3 9 10 11 1 5 3 4. So 2 9 6 46920. 46920. So this is what we have got after multiplying the HCF and LCM. Now product of the numbers. Product of the numbers is equal to, what are the numbers? 510 and 92. Do the product. It has to be 46920. Okay. 92 and 51. This is 92 to 10, 1, 92, 56. 296, 469, 46920. Isn't it? We got it. So in both the cases we are getting the same answer. Therefore, just write. Therefore, HCF into LCM is equal to product of the numbers. So we got it. So you are having two more sums in this particular, under this particular question. So you can go for that one the same way. Okay. Now coming to the third question. Find the LCM and HCF of the following integers by applying the prime factorization method. Same only. Okay. You have to find out the HCF and LCM and then by the method of prime factorization. So these are very easy for you. Then also I will be discussing one question. Let's start. Which one shall we take? Okay, I am taking the first one. Question number 3. Under question number 3 I am taking the first one. The first question is 12, 15 and 21. 12, 15 and 21. Let's start. 12, 15 and 21. So we are having this three numbers. Okay, 12, 15 and 21. So do the prime factorization of 12, then 15, then 21. 2 6 are 12, 2 3 are 6, 3 5 are 15, 3 7 are 21. Done. So we can write 12 as 2 into 2 into 3, 15 as 3 into 5 and 21 as 3 into 7. Now which one will be the HCF? Highest common factor. That has to be a factor which is common to all. See here, 2 is not common, 3, 3, 3. So HCF is 3. Now regarding LCM, what we have told earlier. In LCM, we are going to take that thing which is common to all of the numbers once only, and the remaining all factors we have to take. So from the first one 2 into 2, from the second one 5, from the third one 7, isn't it? So what we are getting ultimately, 3 2s are 6, 6 2s are 12, 12 5s are 60, 6 7s are 42, 420. Okay, 3 2s are 6, 6 2 are 12, 12 5 60, 60, 7 6 are 42, 420 is the LCM. So we got the HCF and LCM as 3 and 420 respectively. So with this one we have completed this exercise, this question. Now question number 4, given that HCF of these two numbers 306 and 657 is 9, find LCM. In that question you have to use that particular idea only, that the product of two numbers will always be equal to the HCF and LCM. Using that particular idea you can proceed. The question number 5. Check whether 6 to the power of n can end with the digit 0 for any natural number n. What they have told is, we have to say, or we have to check whether 6 to the power of n, any number, suppose it is in the form 6 to the power of n, we have to see whether it can have such a number, the value of this is can ultimately be in such a form that its unit digit is 0. It can end with 0, isn't it? So we have to check whether any number which is in this form will end up with 0, means its unit digit is 0 or not. Okay. Now before moving there, now we have to ultimately find check whether the digit in the units place is 0 or not, isn't it? So what you know about a number which is divisible by 10? Suppose the smallest number which is divisible by 10 is 10 itself, isn't it? So when you are having a number which is having digit in the units place as 0, then definitely this number should have 5 in one of the factors as 5 in, isn't it? At least one factor should have been 5. It should be divisible by 5. If a number is ending in 0, definitely it will be divisible by 5. Now if it has to be divisible by 5, it means that it should have at least 5 as one of its factors, isn't it? Any number which is having units digit as 0 will be divisible by 5. It means that it has to be it means 5 has to be a factor of this particular number. Now in this case, see 6 to the power of n, what we can write? 6 to the power of n can be written as 2 into 3 whole to the power of n. It means that 2 to the power of 3n and 3 to the power of n. Now what does this mean? That when I am doing the prime factorization of this number, I am getting only 2 and 3 as its factors, as its prime factors. And by fundamental theorem, just we have discussed earlier, fundamental theorem of arithmetic, that there exist unique prime factors, isn't it? Though their order may be changed, but prime factors will be unique. So by the uniqueness of fundamental theorem of arithmetic, we can say that this particular number is not having any other prime factor other than 2 or 3. But if it would have, it has to be a number which is ending in 0, it should definitely have 5 as one of its factors. But in this case, we are getting none of the factors to be 5. So ultimately what we can say, that it will definitely not end up with a digit in the tens, 0 in the digit 0 in the tens place. Okay, tens place, not ones place. Okay, means its units digit will never be 0. Clear? So how to write that one? So we have to discuss it. So you can start it like that. Since we know that a number which ends with 0 will have 5 as no need to write since here. Okay, we'll just write we know that, since we will be using late. We know that a number which ends with 0 will be divisible by 5. It implies that 5 will be a factor of that number. But here what is happening here? 6 to the power of n is equal to 2 into 3 to the power of n, that is equal to 2 to the power of n into 3 to the power of n. So it implies that 6 to the power of n has only 2 and 3 as its prime factors. 6 to the power of has only 2 and 3 as its prime factors. Why I have written only 2 and 3? By because these are unique. Okay, by uniqueness of fundamental theorem of arithmetic. That's why I have used the word 6 to the power of n has only 2 and 3 as its prime factors. Now, if it is having only 2 and 3 as its prime factors, definitely you are not having 5 as its prime factor, isn't it? So, it implies that 6 to the power of n does not is not having 5 as its factor. If it is not having 6 to the power of 5 as its factor, therefore 6 to the power of n, as it has been given in the question, you go and follow that particular language only. Okay, therefore 6 to the power of n will never end up with the digit 0. Okay, will never end up with the digit 0, means it will never have 0 in its units place.